Okay, so I'm going to get started. Hopefully everyone is aware that we have an exam tomorrow night, 7 to 9 p.m. in Chem 140. Oh, and also the sapling chapter 22 is due 9 a.m. Friday. So, like always, it's due after the exam that covers it, but it's in your best interest to get as much of it done before then as you can. Okay, questions about those? All right, cool. So today I will not be starting the next chapter. I will be just doing a bunch of synthesis reviews. So maybe think of this as sort of an extension of the exam review session, but a little more synthesis heavy. Which, by the way, the recording of the exam review should be posted online. I haven't actually checked. Has anyone gone in and looked to see if it's posted? No? Okay. Well, it should be linked from the course website, but if it's not showing up, let me know and I can contact OIT. Okay, cool. So the last thing from the chapter notes is a synthesis practice problem, so I'll probably do that one first, and then we can look at some other options. Okay. So chapter 22, synthesis practice. So the one I have in the notes is this thing. Okay, so the only requirements I give here are make it from anything with 6 carbons or less. Okay. So I guess your first instinct looking at this is we've got some ketone, we've got an alkyl group hanging off of here. Could we just draw a disconnect here and then have this be a group that so this plus the corresponding alkyl halide. All right, so this is SN2able, so that's not a problem. But what is a problem is we don't really have any selection over which side gets alkylated. Neither side is really the kinetic or the thermodynamic enolate. They're both equally substituted. So if I try hitting this thing with LDA, I've got about equal odds that the new group will add to here versus here. So that's not a really good choice. So it could add either place. So we're going to have to get that group on there some other way. Also, this is 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons anyway. So we're going to have to bring this thing together from pieces at some point anyway. We might as well do it in a way so that we only have one choice of where to add something when we alkylate, and then bring in the other half of the molecule in sort of a more controlled way so that we're limiting the options of alkylation. Okay, so any questions about kind of that issue and how we're going to get around it? Okay, I guess the how we're going to get around it part is what's coming up next. So. Okay. So, instead, maybe let's try drawing our disconnects. Next to the carbonyl instead. We know that we can add alkyl groups onto the base of a carbonyl. So instead of adding something to the alpha carbon as the step immediately previous, which is more like chapter 22 chemistry, maybe the step immediately previous was something more out of chapters 20 and 21. So maybe we're drawing a disconnect maybe here. We could actually do it over here, but then the problem is the chunk that we're breaking off is 1, 2, 3, 4, 10 carbons total, so that's not really getting us below the limit. We could put this together, but if we can split one side off and have it be already under the 6 carbon limit, 1, 2, 3, 4, 5, that might be the easiest way to break it up. Okay, so how are we going to do that? Okay, so we need some kind of carbonyl kind of thing out here. Don't know what yet. And we need some kind of alkyl group over here. Again, not entirely sure how that's going to look when we stick them together. I guess looking at this, we know that we're going to want to add a single R group onto the carbonyl. If we want to have it looking like an actual carbonyl afterwards, could I do this, like use an alkyl lithium and just attack like, I don't know, ester or something like that, or a Grignard and an ester? Would that work to get me what I want? So it would attack once, like I would totally get one alkyl group on here, but what do we know about like Grignards and lithiums with esters? Like they have a leaving group that kicks out and then a second equivalent adds, which is not what I'm going for. Okay, so this setup is not great. That's going to add twice. What I could do instead I actually have a couple workarounds. I put one specific one in the notes, but maybe if that doesn't come to mind when you're looking at this, maybe let's try another option that would also work great. Maybe what I'm going to have to do is not aim for having a carbonyl right after the addition step. Maybe I'm just going to limit this to something that adds once. So one way to do that would be, all right, I'm going to stop drawing out the aromatic ring. One way to do that would just be use an aldehyde in the lithium, or an alkyl lithium. This is going to add once. It's not going to get me the carbonyl that I want right off the bat. But what can I do to convert that back to a carbonyl? PCC, right? Or Jones, either one actually is fine here. Okay, so that's one option to limit it to a single addition, is just use the aldehyde and then work or worry about oxidation states later on. The other option is, if I want to specifically come out of this with the carbonyl already there, we actually have ways to do that too. So if you remember, when we covered Grignards and lithiums plus esters, we covered another way to use organometallics on carbonyls that only adds a single organometallic, and that is cuprates plus acid chlorides. So in that case, we could set it up like an acid chloride, and then a cuprate that looks like whatever alkyl group we're trying to add. And that's just going to add the once, and it'll have the carbonyl right afterwards. Okay, so two different ways to do that. Either one, totally fine. I guess the top one is one more step, but no big deal. Okay, so questions about either parts of that? Uh-huh.
Could you do an alcohol reaction on this?
You could, but yeah, I guess, yeah, that would be doable. Maybe let's finish like getting both of these back to things that are under the limit, and then poke around at aldol a little bit and see how to make that work for the synthesis. Okay, so so I guess since we drew the disconnect in the same place for this option and that one up there, I'm going to work backwards from these precursors. Working backwards from those ones is going to be pretty similar, only you've got, an acid chloride versus an aldehyde or whatever. But all of the bond forming stuff is pretty much done by then. So, or like the actual carbon skeleton is in place in the same way for either option. Okay. Alrighty, so if we want to make, all right, so this thing we would have to make from things fewer than 5 carbons. So that's just I guess pentyl lithium, and then copper iodide would make the cuprates, so that's now under the 5 carbon limit. This one now is where we can start looking at alkylation. So we didn't look specifically at any ways to alkylate acid chlorides. I'm not sure if that would work very well. I feel like the acid chloride is so reactive that probably messing around with base might just go for the carbonyl instead. But we have done stuff with esters, so maybe let's have this thing come from the ester. And now we can stick that on by alkylating at the alpha carbon. Okay. And so this is now 1, 2, 3, 4, 5, 6. I guess I chose ethyl ester kind of by default. Luckily, that just sneaks me in under the 6 carbon limit. If it were one too many, I could just go with methyl, and it doesn't really matter because it's going away anyway. Okay, and then the last part is this thing. I have to get 1 fewer carbons on. So I'm going to have to make this from benzene. That might be a couple different steps, actually. Let's work through that. Okay, so I can make this by halogenating with NBS at that position, and that gets me just toluene here, which I can make from benzene, which is under the 6 carbon limit. Okay, so let's put this together. I guess any questions about why I chose the disconnects the way I did, or sort of where I'm going with this? Yeah. Okay, cool. Let's put it together like start to finish, and then maybe we can talk about any weird issues that come up. Okay. So I'm going to start with benzene. We're going to alkylate it by Friedel-Crafts. Then we're going to halogenate that. Okay, so because we're making a couple different chunks for this molecule that we're sticking together, you can either sort of like go aside in one part of the page and say like, I'm making this section that I'm going to add, I'm going to call it A, and then later on when it's time for it to show up, you can just write like A on the arrow, or you can draw this again and say like C above box for how to make this, or something like that. Or you can have like multiple converging arrows that bring together multiple reagents. Whatever, you know, as long as it's the grader can understand what you're saying, then you're good. Okay, and then also we gotta make the cuprate because it's too big, Elsa. Okay, so there's our cuprate made. I guess maybe we could call this B if we wanted. Okay. So now we can start the actual synthesis part. Okay, so we want to alkylate at the alpha carbon. LDA is probably the safest way to do this. So LDA first, and then we're going to bring in our alkyl halide. Which gets us that. Then we have to convert this thing to the acid chloride. We can't actually do that in one step, so we're going to have to go through like the parent acid first. So let's just hydrolyze that off. So like that, and then SOCl2. Gets us here. And then we can bring in the cuprate with a water workup afterwards. Oh, looks like I left off the water workup on the notes, but it would give us, this is the final product. Okay, so that's if you are doing the chloride plus cuprate. If you're doing the aldehyde plus organolithium, it's pretty similar, just you would want to start with the aldehyde here and go through, or you could start with the ester, alkylate it. That might work a little bit more safely because then you might not have aldol stuff to worry about, and then convert that to the aldehyde and then go from there. So,
With the aldehyde, you don't need the LDA step. Or will the aldehyde be the phenol, the enolate?
Yep, yeah, so the aldehyde would also make the enolate. So LDA should work fine there, I think. So, yeah. Okay, so any questions about this one? Yep.
Can you use hydroxide instead of LDA for this?
Well, I guess rather than hydroxide, you would want like ethoxide, so it doesn't do the, yeah. Yeah, I think that would work okay too. So, yeah, just like, yeah, if you used hydroxide, you just get the carboxylic acid out and then all of your base gets chewed up, so, yeah. Okay, so getting back into your question from earlier about could you do this from aldol? Okay, so the most sensible way to do that, the way that splits it into a chunk that's not over the 6 carbon limit, looks to me like this is the way to do it. So what I'm thinking is, if we had an alkene here before, then this could have been done from this molecule plus this molecule. Okay, so to explain how I'm figuring this out, if you do an aldol condensation, you end up with an alkene conjugated to a carbonyl. I could have gone on either side with that, but I kind of want to lop off like the biggest chunk of the chain that I can manage, just because that'll get me, closer to working backwards. If I just did the double bond over here, I'd only be cutting off 2 carbons, and then I'd still have to build this whole thing myself. So I'm going to try putting a double bond here, which makes this look like an aldol condensation product, which means that when I draw the disconnect here, this side got attacked, and this side did the attack. And this actually came up at the review session yesterday, but I think I'm going to go over like identifying which side is which in a sort of more systematic way, because like being able to look at something and immediately know who attacked who is kind of useful. But I'll get to that in a second. All right, so this side got attacked. This side is doing the attack, specifically from this carbon here. So would this work as a setup? So this one is going to have to be the kinetic enolate because it's on the less substituted side. So yeah, we can manage that with LDA. We bring in LDA, it deprotonates out here. And then this one looks pretty attackable. It's an aldehyde. So yeah, that would work as a pretty good setup. And then we would just have to heat it up afterwards to get the actual condensation to happen in the double bond to form. Okay, and then we've got 1, 2, 3, 4 carbons. So this bit is under the limit. And then we just have to figure out how to make this thing from anything under 6 carbons. Okay, so questions about how I'm pulling that part apart? Yeah?
Is this it's going like directly to the condensation, do you need to show it as a separate step, or can you just like talk about
Oh, you can just show it like present the whole time pretty much, yeah. I guess one thing I haven't really talked about with like considerations for using LDA, a couple people asked me in the exam key, kind of a side box there. A lot of the time it says LDA minus 78 degrees Celsius. That's kind of the standard temperature that you use LDA at. I've sort of left that off all of the arrows where I write LDA, but that's kind of a real common conditions that goes along with it. So, okay. So if you see LDA minus 78, for our purposes, we're just going to write LDA and not worry about temperature. Obviously, in practice, that I don't know what would happen if you tried using LDA at room temperature, but probably nothing good. But I figure there's other conditions that are more important to, or, we have sort of neglected talking about temperature and some other things. We pretty much just use generically heat, so I'm kind of doing the same thing here.
in the like first synthesis you did, not the one with the alkyl reaction,
Mm-hmm.
how did you do an acid workup?
So, actually, yeah, good question, because once the first cuprate attacks and we kick out the chlorine, there really isn't any negative charge left on the molecule. Yeah, so I guess like you could do the aqueous acid workup just to clean up. Okay, that must be why I left it out of the notes, but yeah. I guess in this case, you would not need the acid workup to protonate your molecule because it's already neutral coming out of it. So, good question. Okay. Any other questions before we get back into this one and finish it up? Okay, cool. So this bit is good. We're done there. We still got to figure out how to make this half. 1, 2, 3, 4, 5. Okay, so if we can do this from alkylating this molecule, that might be an option. I guess the problem is alkylating ketones tends not to work great, but yeah, I'll still accept it on an exam, I guess. Just because once you make the enolate with LDA, do I want the kinetic or thermodynamic enolate though here? Yep, I want the thermodynamic enolate, so I'm going to have to use slightly less than 1 equivalent of LDA. So I want the more substituted H removed. Okay. So let's put this one together start to finish. So first LDA 0.95 equivs, or slightly less than 1 equivalent. And then that's going to make the thermodynamic enolate here. And then we can bring in the alkyl halide, which I guess I showed up there as A. So let's reuse that. Stick the alkyl group on there. So like that. And now from here, I'm again going to use LDA because I need to be picky about what happens where. In this case, I want the kinetic enolate. So in this one, I want LDA. I can either just write LDA, which is assumed to be an excess unless we say otherwise, or I can explicitly write excess LDA. Either one of those is fine. Okay, so excess LDA means I'm going to get the kinetic enolates, and then I can bring in the other thing I want it to attack. And that should get me I'm going to draw it out this way first, and then we can tweak it a little bit. So that, if I want, I can say H3O plus to protonate the product, and then heat to force the elimination. And that would get the actual condensation product going there. Okay, and then the last step on this is going to be getting rid of that double bond, which we could swing with just H2 and PD on C. Okay, so 1, 2, 3. Oh, nice. That's actually a shorter synthesis than the one I have in the notes, so good call. Okay. So other questions about this? Okay, cool. So one thing I did want to cover from the exam review session, yeah, I got time, is looking at a product and figuring out what attacked what during the reaction. So retrosynthesis for enolates. So as kind of a general rule, the molecule that makes the enol or the enolate and does the attack stays at the same oxidation level start to finish. And this is not like formal oxidation state or anything. It's looking at like how many bonds to oxygen or more electronegative atoms does the carbon have. So if it starts at the 3 bonds to O state, it's going to end at the 3 bonds to O state. So like esters stay as esters if they're the ones that attack, ketones stay as ketones. The molecule that gets attacked loses 1 oxidation level, so it drops down by 1. Or possibly it drops by 2 if we're doing condensation. Okay. So, and I don't think I included this yesterday, but the disconnect is going to be right next to the base of whatever got attacked. Okay. So if I give you this, so I've got this carbon here has 3 bonds to O. This one here has 2 bonds to O. Odds are pretty good that they started out at the same oxidation state, and this is the one that got attacked. And this is the one that did the attack because it's still got all 3. So I'm going to draw the disconnect next to the base of the one that got attacked right there. Okay, so the way this reaction must have looked was this was doing the attack, this makes the enolate. And then it must have attacked something that looks like this, but with one more bond to O. So probably an ester. Okay, so this enolate attacks this ester. And that's the product that I get. Okay. A lot of the time I'll set these up so it's two identical copies of a molecule because that's the easiest way to avoid multiple different outcomes, but that won't necessarily always be the case. If you're trying to do crossed aldol or crossed claisen, then LDA is generally a good way to set it up so that you minimize byproducts. Okay, so questions about this example? Okay, cool. Let's look at one more. Actually, maybe a couple more. Okay, so like this thing here, I've got something with 2 bonds to O and something with only 1 bond to O. Probably this one got attacked. And so the disconnect's going to be here. And so this comes from this doing the attack. And this getting attacked. So again, 2 copies of the same molecule. Okay, so again, because it's 2 copies of the same thing, you could just set it up as this, and you could use LDA, but that's kind of overkill and unnecessary here. I guess just use base and water. Okay. Would an acid catalyst work okay for this to get the product that I want? Correct. It would not work because in acid it favors the the condensation product, and so you're not going to get the actual aldol coming out of it afterwards. Okay. Questions about that one? Yep.
If you're looking at an asymmetrical molecule, how can you tell?
So something like maybe let's look at this one, for example. Okay, so again, 2 bonds to O, 1 bond to O. This is the side that got attacked. I'm going to draw the disconnect right next to it. So this is going to come from this does the attack. And this gets attacked. All right, so I guess figure out the pieces that it comes from first, and then looking at those will tell you how fiddly you need to be about the other reagents that are involved. For this particular example, so this is the only one that can do the attack. There's no alpha H's over here. And so this is going to attack this one. But the problem is this is also pretty attackable. Like this is the only one that can do the attack, but either one of them could get attacked. So you might have a bunch of byproduct where this thing attacks another copy of itself. So probably LDA is the safer way to go here. So this, hit it with LDA. I'm making the kinetic or thermodynamic enolate, or neither. I guess I'm making the only possible enolate, which is right here, so I don't know if I'd describe that as either kinetic or thermodynamic. So LDA first to butyrprotonate, and then bring in the other molecule, and that should get you the product that you want. Okay, so I guess breaking it down into chunks first and then figuring out how to make the chunks do exactly what you want and nothing else is kind of the sequence of how you want to work through these. Okay. Other questions about, yeah?
Could you give us one where, say, the last exam or the last one had instead of its OH group, it would be carbonyl?
Sure. Yeah, good question, because there is one like that on one of the previous exams. I forget which one. Okay, so there's no obvious choice of roles for either half of this molecule now because they're both in the 2 bonds to O state. So I could actually break this down 2 different ways. One is, maybe let's draw the disconnect here. Maybe let's say the left side got attacked, the right side did the attack. So if I draw the disconnect there, this must have had 1 more bond to O beforehand. Let's make that an ester. And this was pretty much the way it looks now. So like that. Or I could just as easily try putting the disconnect here, which would come from this one doing the attack and a 1 more oxygen having version of the right side getting attacked. So okay. So that's my 2 different options for who does what here. Looking at these, that was a lucky choice of starting material. Okay, well, so in this case, pretty much the only proton here, the only alpha proton here, is going to come off from this location, and it's going to go attack on here. There's like no other possible combination of anything attacking anything else because this is the only alpha H's in the whole deal, and this one is a lot more attackable on account of having an H and an OET than this ketone is. So pretty much if I just throw these 2 things in together, I would expect to get actually just the product that I want. So I might not even have to use LDA, although I could if I wanted to. I think if I just threw these in with like, maybe let's be a little more specific, NaOET and HOET, that should give me the product. Down here, it's actually kind of the same deal. Like all of the H's that I want are the only H's that I have as options in the molecule. Although then this thing could go attack another copy of itself because it is pretty electrophilic being an aldehyde. So this might be the slightly less convenient setup because here I might want to use LDA to be safe, kind of like I did up here where I'm worried about like 2 copies of the aldol getting together. Same thing here. So maybe at this point I would have to do first LDA and then bring in the other guy. And that should still get product, but if you can get around using LDA and just use this cheaper, easier stuff, why wouldn't you? So, okay. Uh-huh.
In the first example, before you had the 2 carbonyls, if you wanted to do condensation in that, you would just add heat.
Uh-huh.
But then when you have 2 carbonyls, is that a possibility, or would you have to?
No, you'd have to reduce one of them down, yeah, with sodium borohydride. And actually, that would be pretty finicky to do because sodium borohydride is going to go after either of them about as fast. Like, we didn't really talk about this technically because this one has the bigger delta positive. Sodium borohydride would go for this one first, but I don't know if there's that much of a difference in rate to where you'd actually trust it to just go for the one you want and then like pull it out of the reaction fast before it goes for the other one, you'd probably get a bunch of stuff out of that. Uh-huh.
Is there any reason for the first example you just did that?
Mhm.
Is there any reason, because you have a like OH group,
Uh-huh.
if you still wanted to make, could you do that whole thing, but making the product down below is supposed to be PCC?
Yeah, I don't see why not. Yeah, if you wanted to like tweak the oxidation states afterwards with like whatever reducing or oxidizing agents, you could totally do that. So that might be making like a little bit harder to apply this stuff because now we're not trusting like is the oxidation level that's actually currently on there the one that it had when it came out of this reaction. But that also opens up some more options like, you know, if you can fiddle around with the oxidation levels, that gives you access to maybe some other stuff through aldol and Claisen that you didn't have before. So.
I'm a little confused on the difference between the NaOET and the LDA. Why that discrepancy?
Yeah. So I guess the big difference here is this is the only thing in this mixture that can do the attack. It's the only one with alpha protons. And this is much more attackable. So this one only attacks. And this one only gets attacked. The difference is here, this one attacks, but it's also fairly electrophilic and attackable. So this one could also get attacked potentially, which means that we're going to have to worry about byproducts and we're going to have to use LDA to cut down any possibility of that happening. Just because like this thing and this thing probably have like, this one is the bigger delta positive on here because we know aldehydes are more reactive than esters. But here, this one has the big delta positive and this one has relatively small delta positive as well. So the one that we want to attack is the one that's already more attackable here. Mm-hmm.
So if you added LDA to like the first month there, would anything change like product-wise?
Nah, LDA would also be totally fine as a way to set that as.
Just add it no matter what, just in case if you don't know. But
Yeah. Like if you're ever unsure, like LDA is not going to be wrong, but yeah, on paper, like LDA is totally good and fine for either of these. I guess in the lab, like if you can get around having to use LDA in person, it's probably better. But yeah, it's either one's good. Yeah.
what's a good way of figuring out if it can attack itself?
So I guess in general, aldehydes are more attackable, more electrophilic than ketones or esters. So this is kind of that continuum of reactivity thing that I had at the start of like the chapter 20 notes, I think. And so whenever you make an enolate from something else, like evaluate the other carbonyls and the other stuff that's around and see like how big a delta positive is on each of them because that might affect what ends up getting attacked by the enolate. Okay. So other questions about this? Okay, cool. So I don't know if I have time to actually do any like full synthesis problems after this. If you guys want, we can wrap it up early and then, yeah, let me know if you have any questions. I got office hours this afternoon. But yeah, let me know if you need any more help with synthesis.